Hello everyone. In this session, we will explore a very important concept in ARM processors, that is ARM addressing modes. Addressing modes define how the processor identifies the location of data, and mastering them is essential for writing efficient ARM assembly programs. So this topic is important for writing assembly programs. So let's recall the last class topic. So that is ARM processor follow a load store architecture. This means data must be moved between memory and registers using explicit instructions. As a result, addressing modes become especially important because they determine how quickly, flexibly and efficiently memory can be accessed. And today's topics for discussion is introduction to addressing modes and the types of addressing modes, that includes the immediate addressing, register, PC relative and advanced addressing modes, that is offset, pre-indexed and post-indexed addressing modes, multiple register transfer LDM or STM, and the demo linked list traversal power of ARM addressing. Now we see about the why addressing modes matter. So addressing modes are crucial for the three main reasons, that is performance, code size and flexibility. First we see about the performance. They allow direct memory access with fewer instruction cycles, which improves the execution speed. Next one is the code size. So the ARM instructions are designed to be compact and efficient addressing modes. So it reduces the number of instructions needed. And third one is the flexibility. So different addressing modes support diverse data structures like arrays, linked list, stack and buffers. In ARM 7, the memory can be accessed only using load and store operations. So understanding addressing modes is essential for efficient programming. Now see about the first addressing, that is immediate addressing mode. The immediate addressing is the simplest form of addressing mode. Here the operand value is directly embedded inside the instruction. So it is indicated as with the hashtag symbol. So that is add R0, R1, hashtag 10. Here the ARM supports rotated immediates, that allowing a wide range of 32-bit constants to be represented using 8-bit patterns. So for example, move R0, hashtag 0xF60, it sets the loads a large constant into R0. This enables a compact and efficient representation of constants inside the instruction itself. And the next addressing mode is the register addressing mode. The register addressing uses data stored in general purpose register. This is the fastest form of addressing, since accessing registers is much quicker than accessing memory. A common example is add R0, R1, R2. That is R0 is equal to R1 plus R2. The values presented in the R1, R2 will be added and the result will be stored in the R0. The register addressing is ideal for arithmetic operations, logical operations and data transfers that occur frequently during program execution. The next one is the PC relative addressing mode. The PC relative addressing calculates the targeted memory address based on the program counter. So for example, LDR R0, open bracket PC hashtag 0x20. Here the effective address is the current PC value plus an offset value. So this method is essential for position independent code, so which allows the programs to run correctly even when loaded at different memory locations. Register indirect addressing like LDR R0, comma, open bracket R1 close bracket uses a pointer stored in R1 to load data. So PC relative addressing is commonly used for accessing constant labels or jump tables. And next one is the advanced addressing modes, that is offset, pre-indexed and post-indexed. ARM supports powerful addressing capabilities for efficient memory traversal. The first one is a ARM offset addressing mode. So it accesses memory at base register plus offset. So it does not update the base register. For example, LDR, that is load R, R1, hashtag 4. Next one is the pre-indexed addressing. So it calculates the base plus offset value, updates the base register automatically. So which is indicated with the exclamation such as LDR R, R1, hashtag 4 close bracket exclamation. And third one is the post-indexed addressing. It loads from the base register, then adds the offset afterwards. For example, LDR R0, R1, hashtag 4. So these are all extremely useful for array indexing, pointer arithmetic and stack operations. Next one is the multiple register transfer, that is LDM bar STM. LDMIA is a load multiple increment after. Example, LDMIA R0 hashtag R1 to R5 loads several registers sequentially. Next one is the STMDB, store multiple decrement before. It typically used for stack operations. So these instructions are very efficient to context switching, block transfers and saving register states during interrupts. They reduces the number of instructions required for bulk memory operations. And this is the prototype stage of design thinking, that is linked list traversal. Simple example to demonstrate the effectiveness of pre-indexed addressing. Assume R1 contains the address of the current node. The instruction LDR R0, R1 hashtag 4 does two things at once, that is loads the node's data, updates R1 to point the next node. So this compact operation makes linked list traversal fast and clean, reducing the overhead pointer, updates the inside loop. And next one is the prototype, that is optimizing memory copy loop. And here it provides the dual pointer movement, optimizes each iteration and reducing instruction count and improving the throughput. And the next one is the power of ARM addressing mode. The power of ARM addressing mode, load store multiple for fast context switching, offset, pre-indexed and post-indexed modes for efficient data structure traversal, immediate register and PC relative addressing mode as a foundational tools for any ARM programming. Mastering these modes leads to compact, high performance and highly optimized assembly code for essential embedded and IoT applications. These are all the references for this topic, and thank you.